Good morning, everyone. So today we are going to see the program, which is LCM and HCF of two 8-bit numbers. So LCM. So if we have two numbers, suppose 2 and 4, least common multiple. So what are the multiples? 2 into 1, 2, 4, 8, 16, and so on. Then what about 4? It is 4, 8, 16, 24, and so on. Sorry, 12 is also there. 4, 8, 12, 16, 24, etc. So what is the least common multiple? So out of this common, what is the least one? So 4 is the least common multiple of the two numbers. So the answer is 4. Similarly, if you want to find the HCF, which is the highest common factor, for the same numbers 2 and 4, what are the factors? 1 is a factor, 2 is a factor. Then for here, which is this is 1, 2, and 4. So what is the highest common factor? It is 2. So the answer we need to get is 2. So this is the just recollecting the fundamentals of LCM and HCF. Now let us see what is the algorithm for doing this program. Okay, so let us see the logic for LCM. So like we discussed earlier, 2 and 4, for 2 and 4, the LCM is 4. So how we are doing is we will divide one number with another number. So there is no significance for the order. So we can for the time being, if it is 2 and 4, we will divide 2 by 4 and we'll check for the remainder. So here the remainder is equal to 2. So what we will do is, so this is the first step. In the second step, again, the numerator, that number is added with again with the same number. So 2 plus 2, it is going to be 4. So 4 divided by 4, the remainder is 0. So this numerator corresponds to our LCM. Let us try to see another example. So this is example 1. So in example 2, let us take the numbers 3 and 4. So the LCM of 3 and 4, the least common multiple, it is 12. So let us do our logic. So first it is 3 by 4. The remainder is equal to 3. Then it becomes 3 plus 3, 6 by 4. So the second operation, it is 6 by 4. So the remainder is going to be 2. Then the third operation, it is 6 plus 3, 9 by 4. So the remainder is equal to 1. And for the fourth operation, the number is 9 plus 3, 12 by 4, which means the remainder is equal to 0. The numerator in that case corresponds to LCM. So LCM equals 12. So this is the logic. You can you do the other way also, 4 by 3. So it becomes 4 by 3. First, okay, let us take 4 by 3. So first condition, it becomes 4 divided by 3. So the remainder is equal to 1. In the second condition, it becomes 4 plus 4, 8 by 3. So the remainder again becomes equal to 2. Then the third iteration, 8 plus 4, 12 by 3. Remainder is equal to 0. So this numerator in that when the remainder becomes equal to 0 corresponds to the LCM. So if you see the second in the second way, the number of iterations required is 3, whereas first case the number of iterations required is 4. So if you are dividing the higher number with the lower number, the number of iterations required will be one lesser than the other way. So that is if you are trying to find the optimized code, you can divide the higher number with the lower number. So highest common factor. So we saw in the case of 4 and 2, we got the highest common factor as 2, right? So how can we do it? So again, there is no significance for the division operation. Here also division operation is the main thing. So what we will do here is during the first iteration, let us do 4 by 2. So in this case, the remainder equals 0. When the remainder equals 0, that denominator corresponds to the highest common factor. So denominator is 2, that corresponds to HCF. Now let us do the second way. In the second way, it is 2 by 4. So what is the remainder here? The remainder equals 2. So remainder is not equal to 0. So what will happen is the previous the previous denominator becomes the new numerator and the previous remainder becomes the new denominator. So 4 by 2. Remainder equals 0 implies 2 is the HCF. The previous denominator which is equal to 2 is the HCF, highest common factor. So let us take another example. The highest common factor between 8 and 6. So here also we should get the highest common factors. For this the factors are 1, 2, 4 and 8. Here for this the factors are 1, 2, 3 and 6. So 2 should be the highest common factor. So let us do it. So so in the first operation, so first iteration, we have 8 by 6. So this becomes, the remainder becomes equal to 2. Then we have in the second iteration, the previous denominator, which is 6, becomes the numerator and the remainder becomes the denominator 6 by 2. So the remainder is equal to 0. So the highest common factor is the denominator, which is equal to 2. Now let us take another example, say 24 and 16. So if we have 24 and 16, so in the first iteration, so 24 and 16, 1, 2, 4, 6, 8, 12 and 24. Those are the factors. Here it is 16. For 16 it is 1, 2, 4, 8, 16. So 8 should be the HCF. So 24 by 16 remainder equals 8. In the second iteration it is 16 by 8. The remainder is equal to 0, implies HCF equals 8. We can do the other way also. So 16 by 24. 16 by 24 remainder equals 16. In the second iteration, the previous denominator becomes the numerator divided by the previous remainder becomes the denominator. So 24 by 16 remainder equals 8. In the third iteration, it is 16 by 8. So the remainder equals 0, implies HCF equals 8. So this is the logic for HCF. So in our case, what we will do is we will have like in all the programs, we will have the inputs defined in the locations 4500 for the first number and 4501 for the second number. So this is number 1 and this is number 2. So whatever the numbers we want to give, we can give there. So I have mentioned this in decimal, okay, but the logic is the same for hexadecimal. Doesn't depend on the number system. So for all the so if you want to do the operation, if you want to find the HCF of two numbers irrespective of whether it is hexadecimal or decimal, first convert those numbers to decimal number system, find the HCF and convert it back to hexadecimal. So that is the operation to do. So, and the result you are going to save in 4502. So here you will have the result. Okay, so we'll limit our result to be within 8 bits for the safer side. So what you have to do is you have to implement the logic for LCM and HCF. So those are two separate sections. You can write it as separate programs, so it is okay. So you can write it as two separate programs. The first program will find the LCM of the two numbers and it will display the result. So you will have a set of test cases for that LCM alone, and you'll save the result in 4502 and show that result. Then for the second program, when you run, you have the same test cases for HCF, same or different test cases for HCF, and again you will show the result in 4502. So the logic, I think it is clear to you. Now you can work on the program. The program I will work during the lab class. Thank you. Okay, so let's see the program for LCM and HCF of two 8-bit numbers. So these are two different test cases. So the first one, the numbers are 09 and 08. So if you see both in hexadecimal and decimal, 09 and 08 corresponds to the same number. So the LCM is 9 into 8, 72. 72 in hexadecimal is 48. That is why we got the LCM in 4502 as 48. Then if you see the highest common factor, HCF, it is equal to 1. So when you run the HCF program, you should get 1, and the LCM program should give us the result of 48. Then the next set of test cases, it is now the first number is 20 and the second number is 18. So in hexadecimal, 20, the 20 is in hexadecimal. Whatever we are giving, it is in hexadecimal in microcontroller. So 20, the decimal equivalent value is 32, and 18, the equivalent value is 24. So 32 and 24, if you see, if you calculate the LCM, it is equal to 96. So the hexadecimal, it is equal to 60. Then the HCF is equal to 0.8. So this is what we have to get when we are after writing the program, and when we are executing. This is a set of results. So let us start writing the program based on the logic whatever we have understood. So so the start of the program, it is org00h. Then we will the first number, that is in 4500. So move dptr comma hash 4500 h. So we will get dptr pointing to the first number location. Movex a comma at dptr. So we got the first number in A. Since always the movement is through A, we'll save that to a register. So let's save it to move R0 comma A. Then increment dptr to get the next number. Then again movex A comma at dptr. So we'll get the second number in A. Let's take a backup copy, move R1 comma A. Now for LCM, what is the logic which we are doing? We'll divide the numerator, the first number, with the second number. We'll see if the remainder is 0. If the remainder is 0, then the numerator corresponds to our LCM. So the instruction we have to use is diff AB. So diff AB is the instruction we have to use. So in A we have the second number. So we can have number 1 by number 2 or number 2 by number 1. So in A already we have the second number. So A equals second number. That second number is also, we have taken a backup copy in R1. But B should be first number then, right? So move B comma R0. So first number move to B. Then we divided A and B. So the instruction is CJNE. So you can check whether CJNE, what is the instruction format. So it is equal to CJNE. We'll have the quotient in A and remainder in B. That is as per the instruction. So let me just show you the instruction once again. So the div instruction. So div instruction, it is A by B, and we'll get the quotient in A, and remainder will go to B. And the other instruction which which we are going to use is CJNE. So let's see what is CJNE. So in CJNE, it's given like CJNE A comma the RAM or a data, and RN comma a data. So that is what the instruction it is being given. So diff AB and CJNE is the two main instructions which we have to use. So let's try to use it. So we have the remainder in B. So as per the instruction, we have to use either a register or B. So as per the instruction set which we have, you can check with using this CJNE with B also. But for the time being, yes, let's use B itself. If it doesn't work, you have to move that reminder to A or another register and work it out. So CJNE B comma, we have to check whether the remainder is 0 0. If it is not equal to 0, we have to go to continue. Okay. So if remainder is not equal to 0, then you have to apply the logic for performing the division. If the remainder is 0, we will jump to saving the result. where we are going to save the result. So this is continue, where we are going to write the logic. So if remainder is not equal to 0, what we have to do? The numerator has to be changed. The numerator has to be added with that same number. Numerator plus that number, first number or second number. That is what we have to do. So the numerator actually was in A. But after doing the division operation, the numerator now it's the quotient. Okay, and already we have that numerator number in R1. So the number, so if it is 4 by 3, so if it is 4 and 3, we are trying to find out the LCM. So it is 4 by 3, remainder is 1. Next it should be 4 plus 4. So 8 by 3, remainder is 2. Next is 8 plus 4. So that 4 is there in R1. Okay, but this numerator which was initially 4 and 8, that will be lost because A is being replaced by the this one. A is being replaced by the quotient. So let us try to take a backup copy of A in another register. So let's move R2 comma A, backup of numerator. So we got that in the R2. So now what we will do? We'll again get back that numerator into A, which is from R2. Then we add A comma R1, that number already, that number. Then B is also lost. So we got B. B after division, it is the remainder. So for dividing, we need to get back B. So that B is there in R0. So R0 we already have, that is not being changed. So move B comma R0. Then what we will do? SGEM to continue division. So continue division will be again this one. Yes, here continue division. So what is happening? So we'll get first number in A, that is saved to R0, then DPTR incremented. Second number in A, that is saved to R1. First number loaded to B. Then the numerator is backed up in R2. Then that numerator is divided by the second number by first number is being performed. So we are checking whether it is equal to 0, 0. So let's take the example itself. So we got in 4500, we have 0, 4. In 4501, we have 0, 3. So yeah, in R0 will be equal to, R0 will be equal to 0, 4. Then R0 will be equal to 0, 4. Then we have A, then A will be equal to 0, 3. Then R1 will be equal to 0, 3. Then B will be equal to 0, 4. Then R2 will be equal to A 0, 3. Okay. Now 3 by 4, that is what it is going to happen. 3 by 4. Remainder is 3. It is not equal to 0. So it will jump to continue. It will come here. A comma R2. A becomes R2. R2 is what? 3. Then add A comma R1. R1 already it is 3. 3 plus 3, it is 6. So A becomes 6. Then B is loaded with R0 because B have been replaced by the remainder. So R0 is 0, 4. So R0, B equals 0, 4, which is loaded from R0. Then again it will continue to division. So in division, R2 will be loaded with the value from say from A. So A becomes 6. So R2 will be loaded with the value of 0, 6. Then again B has to be, yeah, already B is loaded. B equals 4. So 6 by 4, the remainder is equal to 2. So again it is not equal to 0. So it comes to continue. A comma R2. So A becomes 0, 3 becomes 0, 6. Then add A comma R1. So 0, 6 plus R1 is 3. So A becomes 0, 9. Then move B comma R0. B is loaded with reloaded with R0, which is 0, 4. Then continue division. Move R2 comma A. So R2 is backup of A. So previously it was 0, 3. It was the first thing. Then 0, 6. Then 0, 9. Then 9 by 3 not equal to 0. Here it comes A comma R2. So A will be loaded with the value 0, 9. Then add A comma R1. So 9 plus 3 12. So B is loaded with the value from 0 4. Then SGEM to continue division, move R2 comma A. So R2 becomes 12. Then div AB. So 12 by 4 0. So if it is not equal to 0, it continues, otherwise it comes here. So SGEM to save result. So we'll in save result, what we'll do, we have to load the value from R2. R2 is our result. Move A comma R2. So we will increment the dptr and we will save movex at dptr comma A. Stem to here. Program ends. So this is the end of the program. So this is the logic. So the only thing what you have to do is, if this command is not working there in write, you can have another register, maybe say R3 or R4, move that B to R3 or R4 and do the necessary operation. Check that. Or you can move that to a memory location, RAM location, say 40H or something, and then 40H or 50H, then to that location, compare that with that location. So CJNE, that whatever location you have mentioned, so 40 comma 00 to continue. So that is the way you can do. Then you need not have this R1 itself. You can have a direct memory location. I have just used the registers, which was easy for understanding. So this is the program for LCM. So that is the program for LCM. So I had mentioned there as program subtraction. So I had copied from another tab, that is why. So I have replaced that with LCM. Now let us see the program for HCF. So let me just copy it because we can reuse some of the instructions. Don't copy it when you are writing. You write it right from the start based on the logic. So in our case, in the case of HCF, so increment dptr up to this point, again there is a division. So from this we will delete, and then maybe from here, let's see. Okay, we'll go line by line. So if we have two numbers, say 24 and 16, the HCF should be equal to 0 8, right? So let us see how exactly it comes. So the first number R0 will be equal to 24. Then dptr incremented, A will be equal to second number, which is 16. Then R1 is the second number, which is again 16. Then B is loaded with our first number, which is 24. Then R2 comma A. So here this is required. So that is what. So we'll delete from this point. We'll write it and then work it out. So what we will do is, so B, first number is there in B. Our logic is dividing the numbers. So div AB. So this becomes 16 by 24. So remainder is not equal to 0. Now we have to check CJNE B comma. Uh, okay. In the previous case, I had written that. So for the time being, I'll rewrite it in using another kind of thing. Move R3 comma B. So you have to see whether this works. If it works, the instruction will be CJNE R3 comma hash 002. If it is not equal to 00, then continue. If it is equal to 00, our process is over. So we will go to stem save result. In continue, what we'll do, so we have compared where R3 is equal to 00 or not. If it is not equal to 00, we'll come to continue. Then the previous the denominator has to be the numerator. So A has to B is the the previous denominator. So how exactly it was? So 16 by 24, when we divide, the previous denominator will become 24, become the numerator, and the remainder is 16. 16 becomes the denominator. So the previous numerator, which was in where? So when we divide A and B, uh, B is lost. So that was the previous denominator. So that denominator we already have in R naught, right? So again we have to reload. That previous denominator has to be moved to the numerator. So move a comma r0. So a will be loaded with that previous denominator. Then the remainder is already in b. So we can do the subtraction. But the problem actually is now this has to be yes. So it's okay. Then again SGEM to continue division. So this continued division has to be here because b will be lost each time we perform the subtraction. So we have to take a backup of that. So here b comma r0. So b will be from r0. So r0 equals 24. Then divide ab. So we got a. A is the second number, 16 by 24. So r3 comma b. So remainder is 16. It is not equal to 0 0. So again a is loaded with r0. R0 is 24. B already we have the remainder 16. So continue division. Move B comma R naught. So R naught will be so again first number saved in yes. So there's a problem here. R naught has to be backed up with B. So continue division will come here. So move R naught comma B. The reason being before doing the division, that whatever b value is there, whatever denominator is there, you have to save it to r naught. Otherwise, after doing this division, that b will be lost. So that divisor has to be saved. Otherwise, the next division operation, the previous divisor has to be loaded to the numerator. That is why I have done this instruction here. So you write it, then you will understand. Okay. So for the time being, so R0 becomes here again from B, which is the initial case, it becomes 24. A is already the second number, which is 16. So 16 by 24. Then we are checking whether the remainder is 0. Remainder is 16. So it comes to continue. Again, A is loaded with R0. So the previous denominator has to become the divisor has to become a, so which is in r0. So a will become 16 sorry 24. Then we'll continue to division. R0 comma b will be the remainder. So the remainder is 16. So 24 by 16 and the process repeats. Now let us take the example in this case. So up to here it's okay. So again here r naught will be equal to r naught is equal to b. So b equals 24. Then div ab. So 24 by so initially it will be doing 24 divide sorry a will be 16 by 24 is what it will do. Then r3 comma b. So r3 becomes the remainder 16 by 24. The remainder is 16. Then is r3 equal to 0 0? No. So a will be loaded with r0. So a will be loaded with 24. SGEM to continue division. In continue division it comes. So r0 will be loaded with b. So what is the value of b? B will be equal to the previous remainder, which is 16. So here I will write, so a will be the quotient, a will become 0 and a will become 0 and b will become the remainder, b will become 16 after the first division operation. So a becomes 24 here. SGEM to continue division. In continue division, r0 is loaded with b equals 16. Then again the next division operation that is to be performed is a by b. So a is 24. 24 divided by 16 is what it will perform. So the quotient is going to be 1. So a becomes 1. Then R3 becomes B. B becomes 24 by 16 equals 8. So B is equal to 8. Then is it equal to 0? No. So it comes here. Move A comma R naught. So R naught will be loaded. So A will be loaded with the value of R naught, which is 16. STEM to continue division. So R naught comma B. So R naught will be loaded with the value of B, which is 8. Then the division operation that is going to be performed is 16 by 8. So 16 by 8, when we are doing it, the quotient is going to be 2, 2 and the remainder is going to be 0. So B is also going to be 0. Then it is equal to 0. So STEM to save result. So save result it comes. So where we have the value, the highest common factor is equal to 8. So where do we have that 8? So after doing this operation, the R3 value is equal to remainder and R0 equals 8. So R0 is the value of B, right? So that R0 will correspond to our HCF. So move a comma r naught, then increment dptr, move x at dptr comma a. So the program ends. So that is the logic for that is the program for HCF. I urge you to write it yourself following the logic. There might be small difficulties, okay, like how to write it. But when you are thinking and doing it properly, you will be able to write it clearly. So this is the program for HCF, and the previous program is for LCM. Thank you.